In this video, we'll look at regression with categorical variables on the right-hand side, and then also interaction terms between two variables. So let's say, starting with categorical variables here, we want to study differences in weekly earnings across race ethnicity groups. So here's a common way this is done in US data. Okay, we have a single variable, race, and that variable might even be coded numerically, but of course the numerical labels are just arbitrary. We really have four groups here. This is actually not just race, it's sort of race ethnicity categories, and this is commonly done in analyzing US data. So we might call the groups white, black, and other race, and then there's a Hispanic category or group as well. So these first three groups, even if we drop the specifier non-Hispanic, it's sort of implied in the examples that you're going to see. All right, so everyone's in exactly one of these four groups. Okay, it's a combination of race and Hispanic ethnicity data. What we should do here is we're going to include indicators for three of the four groups. Okay, we have to leave one of them out because the intercept will apply to that group. So the way this is typically done in analyzing US data is to leave out not the data, not the individuals for white non-Hispanic people, but not include an indicator for that group. Okay, so we have weekly earnings as our outcome variable, and then we have indicators for black, other, and Hispanic, which again, black means black non-Hispanic and other means other non-Hispanic here. Okay, so we have four categories, which we pick up by including three indicators, with one of the groups here, white non-Hispanic, treated as the baseline or omitted group. Okay. In R, if a variable is coded as a factor, then if you include that variable in the regression as an explanatory variable, R will automatically do the right thing there, which is to leave out one of the category indicators and include indicators for all the other levels of that factor. And if I include something like, a data set on an assignment where I want you to look at differences by race ethnicity group, then I'll have coded it as a factor so that you don't have to figure that out yourself. Okay, so this is a regression of weekly earnings on race, but we're going to treat race here as categorical because it's coded as a factor, and we're applying some sampling weights here you see in this ACS data. Okay, here again is that regression model. Notice, this is a saturated regression model. There are four parameters in the model, an intercept and three coefficients on our variables. And there are four possible combinations of the explanatory variables, which is a little bit more subtle than it was in simple regression. But remember, the four possibilities are for white non-Hispanic individuals, 0, 0, 0. For black non-Hispanic, 1, 0, 0. Other non-Hispanic, 0, 1, 0. And then Hispanic of any race, 0, 0, 1. So those are the four possible combinations of those three X variables you could see in the data, and there are four parameters. So the fitted values in this regression will be average weekly earnings for the various groups. Okay. For white non-Hispanic, just go in and set the indicators to 0 or 1 as we work down these rows of the table. And for white non-Hispanic, all those indicators are 0, and the fitted value in the regression will just be the intercept. For black non-Hispanic, set the black indicator equal to 1. You still got the intercept. Now you have the coefficient on the black indicator. But this is 0, this is 0, so the other terms fall out. Other non-Hispanic, again, just switch those variables to 0 and 1 as appropriate. This will pick out, of course, we've got the intercept and now the beta 2 hat. Hispanic of any race, beta 0 hat plus beta 3 hat. So again, the white non-Hispanic group is what might be called the baseline or omitted category or group. Okay, and remember, the observations on those individuals are still in the regression, and that's what's used here to estimate the intercept. And then the fitted values for all the other groups are the intercept plus their respective coefficient, so that you can think of the beta 1 hat as the difference in average weekly earnings between black non-Hispanic and white non-Hispanic individuals in this sample. All right, and then very similar interpretations for these others relative to the white non-Hispanic average. Okay, we'll look at examples of that in class. The other thing we're going to do in this video is just look briefly at interaction terms. Okay, so here's a question we might be interested in answering. Not just do earnings differ, or how much do they differ between men and women, but what does the earnings education relationship look like across sex? Is it different for men and women? Or more specifically here, do earnings increase with education more for men or for women, or is it the same? And we can use the following regression to look at this. You can see we've got log earnings regressed on female indicator and education. And then this is the new thing for the purposes of this video. This is called an interaction term or interaction variable. It's the product of two other variables in the regression. It's the product of the female variable and education. So if you looked at this in your data, it would be a weird looking variable. If the person is male, female will be 0, so the whole interaction variable will be 0. And if the person is female, it would just be years of education. Female would be 1, and you just have years of education. So you could look down the rows in your data set for this interaction term, and it would be 12, 0, 0, 14, 0, 16, 17, 0, etc. Right? Kind of a strange thing to think about if you haven't seen it before, but it leads to a really nice interpretation, which we'll get to soon. Okay, in R, notice you can put log earnings in the regression. You don't have to create a new variable for it. Just do log earn here, and R will understand that as the natural log, which is what we want. And then you can see here on the right-hand side, I've put female times education. And when R sees that, it will do, again, the right thing in this case. And it will include not just the interaction term, but the constituent variables as well. All right, so that one expression here will include the female indicator, years of education, and the interaction term, 3 separate variables. Okay, and you'll see soon in class estimates of this from the endless Y data. Okay, we'll do one more thing here. When you get this estimated regression equation, so we've got the beta hats on here and then predicted log earnings here, to understand what's going on here, plug in female equals 0 to get the estimated regression line for men, plug in female equals 1 here and here to get the estimated regression line for women. For men, pretty straightforward. All right, these two terms go away, just leaving those. For women, again, plug in female equals 1. So you've got beta 0 hat, beta 1 hat times 1, beta 2 hat times education, beta 3 hat times 1 times education. Let's group some terms here. Like so. So what we have is the intercept for women is beta 0 hat plus beta 1 hat. The slope on education for women is beta 2 hat plus beta 3 hat. All right, and I want to point this out as often as I can. Beta 1 hat is not the intercept for women. It's the extra intercept for women compared to the intercept for men in a log earnings against education plot. Okay, beta 3 hat is not the slope on education for women. It's the extra slope relative to men. This is the slope for men. This is the slope for women. All right, so that coefficient on the interaction term has a nice interpretation as the difference in the slope on education. The difference in the slope on education for women relative to men, and therefore it can directly answer our question, how much higher or lower is that slope for women compared to men?